So, good afternoon for everyone. First of all, thank you very much for your time and to be here with us for our algebra seminar. The speaker today is Wilton from Cambridge University. He'll talk about unstable primitivity rank. Please, could you start?
Hello, everyone. It's great to be here. Thanks for the invitation. I think this is my first talk in Brazil, so, and it's much less nice than if I were actually there. But it's nice to have a little feeling of Brazil, just a tiny bit of contact with Brazil. So today I'm going to talk about a new invariant that you can associate to an element of a free group, and it's called stable primitivity rank. And the main thing I'm going to do is I'm going to try to give you the definition of this invariant, and I'll talk a little bit about its properties. And this work is joint with Lars Lauder. So there's a, yeah. Okay. So, so imagine you have a word in a free group, and my free group will usually be called FR, and it might even have some generators, A1 up to AR. It'll be a finitely generated free group. And the first question I'd like you to think about, the sort of the motivating question maybe, is how can we decide if our word W is primitive? And what I mean by a primitive word is a word, that means a word that's in the automorphism orbit of one of the generators that we were given. So it might as well be this A1 that we started with. Right. So, you know, when we define free groups, we often define them with a basis. So we often start by saying they're generated by A1 up to AR, and they're the free group on those generators. So no relations hold between those generators, or they have a universal property, or however you want to say it. And so we know that, so those generators are extremely non-unique. So the automorphism group of a free group is really big, and it acts on the free group, and it'll act on any one of these generators and give you a lot of other generators. And so these are the primitive elements, and they're quite a big set inside your free group. There's an awful lot of them because the automorphism group is very big. And so it's a very difficult task in general to figure out whether or not your word W was primitive. So it could be, it's not a question of you don't just look at the word and say, you don't just look at the word and say, oh, is it of length 1? That's not good enough. You have to, it could be more complicated than that. For example, a silly example is that if I take, let me just write it up here, for example, A1, A2 is a primitive word, right? That's an example of a primitive word. And then I could have, I could multiply that. Let's see, I could do this one to the -7 times A3. That's another primitive word. The 7 wasn't important, and so on. So you begin to get the idea, hopefully, that these are, there's a lot of these primitive words. Right, and so it's a difficult task in general to decide whether or not the word you're looking at is primitive. Okay. Now I want to talk about 2 ways to think about the problem. So the first way is an easy answer that you can try to use, which will not always give you the right answer. And because I like to think about things in topology, I want to call, from a topological point of view, I call this the homological answer. Right? So it's a bit like the homology groups of a space. When they give you the answer you want, they're easy to compute, but they don't, but sometimes they don't work. Right? And so this answer is as follows. Instead of working in the free group, we're going to abelianize our free group. So we're going to look at the canonical map, which takes our free group and maps it to its abelianization, which is Z to the R. Okay. And now if under that map, then we can look at what this does to this word W. And if it turns out that W goes to 0 under that map, then that definitely tells us that W is not a primitive element. Okay. For example, W is a commutator, right? If W is a commutator, so by that I mean A1, A2, A1 inverse, A2 inverse, then that would mean that W is not primitive, because it would go, because a primitive element has to go to a basis element of my abelianization. So that's an easy answer when it works, but frequently it doesn't work. Right? There are lots of primitive elements that aren't 0 in the abelianization. So this answer doesn't always work. So let me give you a different answer, which is a better answer. And I think of it, because I like to think about things in terms of topology, I think of it as the homotopical answer, because it's always, because if you can compute it, then it's definitely the right answer. But it may be more difficult to compute. And I'm actually not going to tell you this I'm not going to give you the full details of this answer. I'm just going to tell you that it exists. Oh my goodness, sorry, I've done the wrong thing. I was showing my screen and I think something happened. Whoa, let's see. Let me see if I can get it back. There we are, it's back. Okay, good. Somehow, sorry, I pressed the wrong thing. Okay, so I'm just going to describe this answer very briefly. So in 1949, Whitehead actually described an algorithm that will answer this question, right? And that's quite impressive, actually, because in 1949, algorithms were a pretty new idea. Right? They hadn't been around for very long. And actually, and I'm not going to tell you how Whitehead's algorithm works today, because that's not important for the talk. But I just want you to know that you just need to know for now that there is an answer to this question, and it's a lot more complicated than this nice, easy algebraic answer of just abelianizing. It's just a much more complicated answer, but it will always work. So those are the two different ways you can try to answer this question. And what I'm more interested in today is talking about some ways of measuring the difficulty of these two answers, right? So some ways of sort of measuring how difficult it is to check that your element isn't primitive using these different methods. Right? So today I want to talk about the difficulty of these methods, right? And first of all, I'm going to talk about the difficulty of the homological method. And this is measured by something called the commutator length, which is quite a well-known invariant that I'll just describe quickly. And I've attributed it to Color in 1979, although actually it was definitely studied before then, but in Color's thesis in 1979, he proved some very nice theorems about it. So his is the name I'm going to mention now when talking about that. And the commutator length of W is what it sounds like. It's the easiest way of writing W as a product of commutators. So it's denoted the commutator length of W like that, CL of W, and it's the minimum n such that W can be written as a product from I equals 1 to n of I commutators. Okay. So that's the definition of the commutator length. So for example, if I gave you, A1, B1, then that has commutator length. Well, let's just say if I give you, if I give you a word like AB, then that has commutator length equal to 1. And if I give you a word like, ABCD, then that has commutator length equal to 2, and so on. Although in general, you should bear in mind that it might be harder. It might be harder than you think. So if I give you, it might be harder than you think to compute the commutator length. So for instance, if I gave you a more complicated word, like maybe, if I just made this AB again, it's clear that that commutator length is at most 2, because we have this. But there might be some other way of writing the word that makes it short, that makes it, that actually, that realizes a shorter commutator length. And that can happen, actually. Sometimes the commutator length is shorter than it looks. So you have to be a bit careful. Anyway. But that's the commutator length. And if you think about it, well, this, you get this kind of expression for your word if and only if your word is 0 in under the abelianization, right? You're 0 in the abelianization exactly if you're in the commutator subgroup, which is exactly if you're a product of commutators, right? So this is somehow measuring how easy it is to check that your word is 0 in the abelianization. Okay. And maybe I'll just say let me give one other detail, which is that, sorry, I've kind of not left myself much space. Let me move this over. One other detail I'd like to say is that, by the way, for me, the minimum of the empty set is always going to be infinity, right? So when I'm going to define this invariant and some other invariants as minima, or even a bit later on, we'll have some that are infima. And sometimes there'll be the minimum of the empty set or the infimum of the empty set. So in that case, we're just going to say that these invariants are infinity. So in this case, so this tells us that, so in this case, this tells us that, oops, sorry, didn't do that right. This tells us that if W is not in the commutator subgroup of F, then I'm just going to say that the commutator length of W is infinity, right? And that'll make sense of some of the statements that I make later. Okay. All right, good. So that's the commutator length. Now, is there an analog of this for Whitehead's algorithm? So so this is somehow a measure of this complexity here. That's a measure of this complexity here, of the complexity of this method A. Now, what about this method B? Do we have a measure of complexity for that? Well, we do. And this is a much more recent definition, and it was defined by Puder quite recently. So it was defined in 2014. So it's a much more recent discovery. And it's called the primitivity rank. And the primitivity rank, so it's called pi of W. And it's defined to be the minimum. Again, it's the minimum of some, actually, I want to say it's, I don't want to say it's at the end. Sorry, I've done that wrong. I want to say it's the minimum of the rank of all the H's such that, well, what are H's allowed to be? Well, H's are meant to be subgroups of my free group F that contain W. But I want to say a bit more than that. I also want to say that W is not primitive in H. Okay. So I can look at all the subgroups of F, and some of them will contain W. And among those, well, W will be a primitive element in some of those H's and not a primitive element in some other of those H's. And so, and I'm only allowed to think about the ones where it's not a primitive element. Okay. So this gives me some collection of subgroups. They all have a rank. They all have ranks, which is some natural numbers. And I'm going to say that the minimal rank, the minimal natural number I see there, that's the primitivity rank. Okay. So this is Puder's definition. You know, for example, I can give you, you know, maybe as another example here, when we looked at you know, if I give you A, B sitting inside the free group generated by A and B, well, the primitivity rank of that guy is going to be 2, because the commutator sits inside, the commutator is not primitive inside this free group AB, and that free group has rank 2, and so that tells us that the primitivity rank cannot be any, you know, the most it could be is 2. And it turns out, we'll see a little bit later on that that's you know, that's as small as you can get, actually, so it's not going to be 1. So that's the primitivity rank. So this turns out to be a really interesting number, this primitivity rank. It seems like a very naive definition, and maybe it's not going to be that useful, but actually it turns out to be really useful. So I just want to mention a couple of the things that have been done with it. So first of all, so Puder and his co-authors have related pi of w to this very fancy stuff. They related it to moments of word measures on symmetric groups. So this is a very sophisticated analysis, which I'm not going to tell you any more about here, but it's a really, you know, it's a beautiful story. I would recommend you, if you want to read it, it's a great thing to go and investigate, but it's very deep. And it turns out that this primitivity rank plays a really deep role. So, and then actually, so Lars Lauder and I, in earlier work, we related pi of w to the subgroup structure of one-related groups as well. So we were interested in groups of the form, you know, A generated by A, where and your word W is going to be the relator somehow. So we're going to be interested in groups of this sort of form. So I'll write it like that. And it turns out that this pi of W plays a role in the subgroups, in the subgroup structure of these groups. So I'm not going to say more about that, but that's, you know, it turns out to be that's another place where this number plays a role. So this primitivity rank seems to be really an interesting number. Okay. Now I want to get more sophisticated, and I want to give a more interesting sort of, I want to look at some even more interesting numbers. Now, so first of all, I want to motivate that by talking about commutator length again. So if we come back to commutator length, you might have noticed that commutator length is subadditive. So what do I mean by that? If you look at the definition, you might notice that the commutator length of U and V, if I look at a product UV, then it just followed from the definition that this is at most the commutator length of U, so at most the commutator length of U plus the commutator length of V. And that you can see directly from the definition, right? Because if I can write U as a product of commutators and V as a product of commutators, then I can write UV as a product of those two products of commutators. And so that's the most number of commutators I could need. Okay. And that motivates the definition of, well, and then I'm not going to talk about it. Can't give you too many more details right now, but it turns out that if you look at a word in your free group, and you look at its commutator length, and then you start taking powers of that word, it turns out that actually the commutator length starts to become smaller than you expect it to be. So you would expect the commutator length of W to the n to be n times the commutator length of W. But it turns out that that's never true, actually. So it turns out that the commutator length of W to the n is always actually ends up in the limit, turns out to be a bit smaller than n times the commutator length of W. Okay, now I'm not going to give you an example of that right now, but I can, because I guess I want to get on. But in order to capture this phenomenon, it turns out that you should you make a definition called stable commutator length. Now, hey, so now this is I wanted to give you this definition, of something called stable commutator length. And the definition of the stable commutator length of W is as follows. You take the commutator lengths of the powers W to the n, right? And you divide them by n. And because this is subadditive, because of this subadditivity property that we had over here, this is a decreasing sequence, right? Or at least a non-increasing sequence. And because of that, it has a limit. And that limit is the stable commutator length. Okay. So that's what the stable commutator length is. And I just want to give you a fact, which is actually that SCL of W is never equal to the commutator length of W. Actually. It's always strictly less than the commutator length of W. So that's a pretty surprising thing. So this turns out to be a really interesting number that you can get from a free group, from an element of a free group. And the thing I want to say about it is I don't want to get into too much into the properties of stable commutator length, but I do want to tell you it's so interesting that Danny Kaligari wrote a whole book about it. He has a whole book. It's called SCL, and you can find it on his website. So if you want to learn more about stable commutator length, it's there's a whole book which is freely available on his website. You can download it, and it's a very beautiful book full of interesting maths. So this is a really interesting number. Okay, these are really interesting numbers. So the problem with stable commutator length, the thing that might make you sad about it, is that commutator length was an integer, right? And that's obviously really useful for lots of things. Stable commutator length is not an integer, or at least is usually not an integer anymore. And so that's pretty disappointing. It means that, lots of, it means you can't use the sort of arguments that you would use that you would normally use about integral invariance. You can't, look at a minimal thing or things like that. But it turns out it does have two important properties that are worth knowing about. So one is called the Duncan Howie Gap. And this is for elements of free groups. It tells you that the stable commutator length of W is always bigger than or equal to a half. Okay. So although it's not an integer, it can't get down arbitrarily small, right? It doesn't just become zero, right? Which is what you might worry about once you know that it gets very small. You might worry the limit is always zero, and so it's not an interesting number. And then another beautiful result that helps us think that stable commutator length is still interesting even though it's not an integer is Kaligari's Rationality Theorem. And here Kaligari proved that the stable commutator length is always a rational number. So although it's not an integer, it is always rational. And of course, that wasn't obvious from the definition because I gave you this definition as a limit. But it turns out it is always a rational number, or of course it could be from what I said before, it's also allowed to be infinity, right? So if your element W isn't in the commutator subgroup, then it will be, this number is infinite. But anyway, it's always rational or infinite. Okay. So that's the stable commutator length. And so my question for today is the following thing. The question I want to ask is there a stable, let me say that slightly differently. Is there an interesting stable analog of primitivity rank? Okay. So we have, commutator length has these two cousins, right? It has the primitivity rank and it has the stable commutator length. And I want to know, is there another cousin, which is the stable primitivity rank, which somehow has, which is to primitivity rank what stable commutator length is to commutator length? That's my question. And I don't really know the answer to that question. But I want to consider three possible answers, right? The first answer I want to consider is no. The second answer I want to consider is yes. And the third possible answer is I don't know. Right? So these are all answers I want to tell you about. All right. Okay. So let's get started. Let's try the answer no. Well, we could try just to make a definition which looks exactly like the definition that we had for commutator length. So we could try, I want to call this whatever stable primitivity rank is, I want to call it S pi. Right? Just like stable commutator length is SCL. And we could try taking the stable primitivity rank of W to be the limit, or at least because I'm not certain it's going to exist, I'll say liminf, let's say liminf, of, as n goes to infinity, of the primitivity rank of W to the n divided by n, right? So that's the definition that looks a lot like the definition of stable commutator length. But we have a problem, right? This doesn't work. The reason is that W to the n is never primitive in FR, right? And so that tells me that, because why is that? Because, well, at least when n is strictly bigger than 1. Okay. Excuse me. That's because powers are never primitive elements. Right? W to the n is a proper power, so it's never a primitive element. So that means that, so therefore that tells me that that pi of W to the n can be at most R, which is the rank of FR, right? Right. And therefore pi of W to the n divided by n is at most R over n. And so that's going to tend to 0 as n tends to infinity. Right? So I gave you, so the trouble is I've just given you a really boring definition because it always defines 0. So that's not much good. Right? So this is not a good definition. So although it is a definition of stable primitivity rank, it's not an interesting one, right? So I failed the interesting test. Okay, this is not an interesting number. All right. So it turns out, and the reason this is true is because I didn't really take a very good definition of stable commutator length. Right? So it turns out that stable commutator length, has another definition, which you can learn about in Caligari's book, but I'm going to tell you about here. And that definition is a better one to try to mimic in order to try to define stable primitivity rank. Okay.
Henrik, may I ask you a question at this point before you go on?
Yes, please do.
I'm a bit confused here because when you said define primitivity rank, right? To the element, you were considering all subgroups that contain this element.
Yes.
And here somehow you fix FR, all right? W, and when you go to the power of W to the n, right? You don't go to subgroups. You just say that it is not primitive in FR, but it can be primitive in some subgroup.
Yeah. That's right. And you're absolutely right that that's why it's a bad definition. Somehow the fact that I raised W to the n should tell me that I should use different subgroups. That's certainly true. But the definition I've given you here, FR is an example of a subgroup that contains W to the n and which W to the n isn't primitive in. Right?
Mm-hmm. So
therefore, according to Puder, pi of W to the n is at most R. Right? That just is true. That's just the definition of the primitivity rank. Right? Yeah. Because if we go back to the definition said that it was a minimum across all of the ranks of H, across all H, where W is not primitive in H. So in particular, FR is an example of such a subgroup. Right? Yeah. Does that make sense, Pavel?
Yeah.
Yeah. Okay. So you're certainly right that this is not a good definition. Right? That's what I definitely agree with you about that. And you're right. You've sort of said correctly what the problem is. Somehow you want to pass to. When you pass to a power, you really want to insist that you're looking at different subgroups at that point. Okay, but here's a one way to talk about that though. So here's a better characterization of what SCL is. But to do it, we have to think about topology. So we have to think about free groups as fundamental groups of graphs. So I want to think about pi1 as the fundamental group of a graph. Right. So here's my graph. It's going to be a rose. So in other words, a graph which is it's got one vertex and it's got, well, it's a wedge of circles is one way to say what it is. So it's got one vertex and R edges, where R is F was meant to be FR, wasn't it? Where R is the number of generators. And when I do this, I can think of my element W as coming from a circle S1 immersed in my graph. Oh, and I want to give my graph a name. I'm going to call my graph gamma. Okay. So that's how I can think of so I can now think about my element W in that way. Just as a circle that maps to a graph. Now, strictly speaking, if I'm thinking about an element of a group, I should put base points in here. If fundamental groups use base points, but actually all of the numbers I've talked about here are really invariants of the conjugacy class of the element, and therefore I don't need base points. So as long as I deal with things that are just invariants of conjugacy classes, then base points are not going to be important. Okay. So the free group FR is the fundamental group of gamma. So from this point of view, the stable commutator length is the infimum of the following quantities. So there's going to be some surface. We're going to think about some surfaces, sigma, and I'll tell you about them in a second. But they're going to be surfaces with boundary, and I'm going to look at their Euler characteristic. Right? So hopefully, Pavel, do you think is it okay for everyone? Okay, know what the Euler characteristic of a surface is, or should I remind everyone?
To professors it is okay. For students, I'm not sure.
Not sure. Yeah. Okay.
Depends on the student.
Yeah. Okay. Well, okay. I'll remind you what this is I'll remind you what the Euler characteristic is in a second. Okay. I'll give you the definition of the Euler characteristic in a second. But for now, I'll just write Euler characteristic. And then I'm going to take, it's actually going to be minus the Euler characteristic, it turns out, because most of the time, otherwise we'd get negative numbers, which we don't want. And then I'm going to divide by the degree, by something that I'm going to call the degree of the boundary of the surface. Okay. And I will now, and now I'm going to tell you what all of these numbers are. Okay, I'm going to tell you which surfaces I'm going to allow, and I'm going to tell you what all these numbers are. But this is this number is the this is the number that I want to consider. Okay. So it's the infimum over all diagrams, and the diagrams are going to be of the following form. So my surface sigma is a compact surface with boundary, which means it looks something like this. Okay. And the boundary is this collection of circles that are sitting, that you can see are sitting on the edge. Maybe I'll draw them in a different color. So here's my boundary, right? And the surface also has the surface has some holes in it, which are which has G holes, right? It has whatever the G are. There's some number of holes, which is the genus of the surface, right? And there's maybe there's going to be B you know, there's B, the number of these circles, excuse me, is going to be, there's going to be B of these. And using this, I can now tell you what the Euler characteristic is. So the Euler, if I just go back up here, the Euler characteristic of this surface, sigma, is going to be 2 minus 2g minus b. All right. So that number just turns out to be a really useful number. So I won't motivate that anymore, but it's a famous number, you know, which goes back to Euler's work on, I don't know, on planar graphs, I guess, along 300 years ago or something, 200 years, 250 years ago. Okay, so this is my surface, and the surface is allowed to map, it just has a continuous map to the graph. Okay. But I'm not allowed to consider any such surface. There's a further constraint. The constraint is that this, you know, over here I have the boundary. The boundary includes, the boundary's over here. It includes into the surface, but that map has to factor. I insist that that map factors through the circle, right? So that factors through the element that I care about. And yeah, so it factors like this. And so actually, yeah, so now what I want to say, once I know that, so I'm allowed to look at all of these, surfaces, right? So there's it's obviously an infinite collection of surfaces, but for each of them has an Euler characteristic. And now I have to tell you what the degree is. So to get the degree, I'm lying a little bit, but this is the basic idea. You look at a point on the circle here, and you count the number of preimages it has in this circle. It has in the circles up here. And so the degree of the boundary of sigma is going to be the number of preimages. Okay. So I'm lying just a little bit about that, but that's essentially correct. Actually, there's a sign. So it turns out you need to assign signs to the preimages. They each get either a +1 or a -1, but I won't tell you about that now because it's not so important. So the degree is it's those number of preimages of a point. Okay. And so this definition, this is the definition. This is the way of talking about stable commutator length, which turns out to be, I know it's a lot more complicated. From an algebraic point of view, it's a lot more complicated than the definition I gave you first, but it turns out to be a much better definition. And in fact, what Kaligari proved, actually, I'm sorry, it is a much better definition, but I got it slightly wrong. It turns out you have to put a 2 in here. I'm sorry, there's a 2. There's just a factor of 2 floating around, which I'd forgotten about, but there it is. You need to put that 2 in there. It's because the 2 is there because it's the same 2 as this 2 here, actually. Oh, excuse me. It's the same 2. This 2, and this 2 are the same 2, basically. Turns out you have to put in a 2 to account for that. And actually what Kaligari proved when he proved his rationality theorem was he proved that actually, from this point of view, this inf is a min. So actually, when you look at it in this way, the infimum is always realized, right, by one of these surfaces. And so that for that reason, because we can see that each instance of this number here is going to be a rational number. Well, of course, an inf of a collection of rational numbers isn't necessarily rational, but a min of a collection of rational numbers is going to be rational, right? As long as it's actually realized. So that's why it's a rational number. Okay, so this inf is a min. So this is the definition that I'm going to mimic to define a better to give a better definition of stable primitivity rank S pi of W. Okay. So I'm going to get started now. So now instead of our surfaces here, so up here we had our surfaces, and you should think of them as, you know, in case that wasn't clear, you should think of them as kind of filled, you know, they're nice topological objects, they're filled in, they're manifolds with, you know, They're nice topological objects. But instead here, we're going to just think about graphs. So I'm just going to map graphs to graphs. So I'm going to consider an immersion of finite graphs. And again, the target graph here, gamma, is the graph whose fundamental group is my free group, FR. But now I'm going to consider, I'm just going to consider finite graphs mapping to it. And now, so now I have a diagram that looks like this. So you see, I've got my, on the one hand, I've got my circle mapping to my graph, which comes from, which represents my element W that I'm interested in. And on the other hand, I also have my, I also have this graph delta that's mapping to gamma. And I can look at this picture, I can look at these two maps, and there's a way of defining a thing called a pullback. And I want to tell you how to do that. So this pullback, I'm going to call it S delta. And it sits in here like this, and I'm going to call this map W delta. Okay. And this, let me tell you how to define this. So actually, maybe I'll give myself a bit more room to define this guy. Okay. So I define it as follows. So there's a thing called a fiber product. And the notation is this, it's S cross delta over gamma. And it's defined to be, I guess I need to give everything a name here. Sorry, so this map here should be, I'll call this map F. It's defined to be the set of pairs of points, X and Y, in the product S1 cross delta, such that W of X equals F of Y. So it's the points, it's the pairs of points in here. I did that wrong. Yeah, I've got 1 point in S1 and 1 point in delta. So they give me together, they give me a point in this fiber product if they both get sent to the same point in gamma. Okay. So that's a thing called a fiber product. And in general, it's going to look, in this case, it's going to look like, because it's sitting above, because it comes with a map to S1. Right, so let me mention, it comes with maps to S1 and maps to delta, given just by projecting onto a factor. And if you sort of think hard enough about the map to S1, you can convince yourself that this guy, what it looks like is it's a union of circles. You'll get some circles and you'll also get some intervals. So in general, there'll be some circles and some intervals. Right? And this pullback that I'm going to define here is going to be obtained. That's what I get just by forgetting about the intervals. So I stop thinking about the intervals and I just think about the circles. Right. So it's just the pullback is just these guys, right? So this is just the circles. This is the S delta that I'm talking about. Okay. And okay. All right. And yeah, and so because this is an algebra seminar, let me also say that, you know, this can be thought of as a collection of conjugacy classes in delta here. So you can think of this. So you can think of this as, you know, you can also think of W delta here, this as a collection of conjugacy classes in delta. So it's not just one conjugacy class; it's a collection of conjugacy classes, and they all live in, not in delta, but in the fundamental group. So in pi1 of delta is what I should say. So you can think of them as a collection of conjugacy classes in pi1 of delta. It's a way of taking a conjugacy class here in gamma or in pi1 of gamma in a free group, and pulling it back to a collection of conjugacy classes in a subgroup delta. Okay. Now, so we say that delta is, I wanted to I now want to make a definition that looks a lot like this definition we just saw for stable commutator length, where I take Euler characteristics and then I divide by degrees. But I can't do that for all of these maps delta. I need to somehow remember, I need to make sure that these W deltas are quite complicated inside delta. That's important. I can't just take any map, any graph delta. So we say that delta is decomposable if the fundamental group of delta can be split as a free product A star B non-trivially relative to W delta. And what I mean by that is that all of the conjugacy classes defined by W delta are conjugate into one side or another. So they either go into A or they go into B, right? Each conjugacy class can be conjugated into A or conjugated into B, but they don't like crash around all the way through pi1 of delta. They have to go on one side or another. Okay. So you can draw, and otherwise delta is called indecomposable. Right. So that's that's what it means for delta to be decomposable, and otherwise delta is called indecomposable. And now with all of this technology, I can give you a better definition of what this stable primitivity rank is. The definition is that S pi of W is defined now to be the infimum I want to say minus chi, so minus the Euler characteristic of delta divided by the degree of this collection of circles S delta, where this ranges over all the delta, over all the indecomposable delta that I just talked about. Okay, so it's like, so this is very much like the definition this other characterization we had of stable commutator length, where we're taking an infimum of minus an Euler characteristic divided by some sort of degree. So let me just tell you what the Euler characteristic, since we're doing, let me just remind you that the Euler characteristic of a graph now, let me just remind you of that. If you're not comfortable with Euler characteristic, let me just remind you that the Euler characteristic of delta, where delta is now a graph, is going to be the number of vertices of delta minus the number of edges of delta. Okay, and that's the definition of the Euler characteristic of a graph. Okay. And now what about the degree? I guess I should just quickly tell you again what the degree is. Well, the degree is going to be defined in just the same way that I said before. So if I come back to this picture here, if I look at, I've got a collection of circles mapping to a circle, and I just choose one point on the downstairs circle, and I look at the number of pre-images upstairs. So I just count, right? Okay, so I just count. So that's the degree. Okay, so that's my definition. Okay, now it's a much more complicated definition, so I'm sorry it's so complicated, but somehow for me it's the best way to say it, and I don't really know a better way of saying it. Okay, but now I need to convince you that this is an interesting definition. Okay, so now, so the previous time I tried to make a definition, it was boring and it didn't give us any interesting answers. So we need to now ask, is this a non-trivial definition? So is there at least some examples where this is trivial, this is non-trivial? And the answer is yes. So if I take my free group FR to be generated by A1 up to AR, then I'm going to look at the word UR, which is going to be defined to be A1 squared, A2 squared, ... up to AR squared. Okay. So that's a reasonable definition for that's a word, some word. And I want to give you a hint as to why what I'm about to say is true. So this is, again, you sort of have to think about it topologically. this is pi1 of a surface, where what is the surface? The surface is a non-orientable surface, which looks like this. You take a surface that looks like this picture here, with a whole bunch of boundary components, but no holes in the middle. And now I glue little Möbius bands. I glue little Möbius bands along their boundary to each of these boundary components, and then I leave one remaining boundary component free, this one here. And this one here, that one is now UR. So that now, if I think at this surface, it turns out it has a free fundamental group, and that boundary component is UR. And it turns out, and I think I won't tell you exactly why this is true, but I'm happy to try to explain afterwards if you'd like me to. It turns out that with this definition, the stable primitivity rank of UR turns out to be equal to R minus 1. So that's good news, because it means it's not always 0. And in fact, it can get arbitrarily large, right? So now, this is some evidence that this definition that I've given you is an interesting definition. It's at least seems like it could be, it has the potential to be an interesting definition. Okay. It takes infinitely many values, so that's a good start. Okay. So now we can ask, well, does this number, does it have any interesting properties like the stable commutator length did? Well, yes, it does. And one of these properties is a theorem from, I want to call it the LWHW gap, and that's because it was proved by myself and Lars Lauder in 2014, and also at the same time by Helfer and Wise. And this says that if W is not a proper power, so if it's not equal to U to the K for some K bigger than 1, then S pi of W is bigger than or equal to 1. So it turns out that S pi of W is so that's very much an analog of the Duncan Howie gap that we had for stable commutator length that I mentioned a while ago. Okay. Now at the time, when we proved this result, there was no definition of S pi. So this theorem, what we proved is these quantities here. What we proved is that these quantities here, these ones here, are always at least 1. And then, so therefore the infimum across them has to all be at least 1. Okay. So that's one. It's an old theorem, but it has a new interpretation in terms of this definition. So today's theorem is a new rationality theorem, and I'm sorry, actually, the sort of so when I gave this talk before, I hadn't talked to Lauder about it yet, and I had a proof in mind, but now, as I said, this is now joint work because we're now doing things with this together. So this is the rationality theorem, and it says that this is the analog of Kaligari's theorem, and it says that S pi of W is always a rational number unless it happens to be infinity. So sometimes it's infinity, but otherwise it's a rational number. Okay. Anyway, and the proof goes along the same lines as what Kaligari does for his rationality theorem. So in particular, it proves that this infimum is really a min. So that's really what it proves. Okay. So that's my stable primitivity rank, and it has some nice properties. And I want to finish by telling you, well, I guess before we go on, I just want to give you some relationships between the quantities that I've talked about. So it turns out that there are some fairly easy inequalities that relate all of these things, which I'll tell you about. So first of all, so for any word in our free group, we can say the following things. So it turns out that actually a better quantity to look at than the commutator length is twice the commutator length of W minus 1. And if I do that, then it turns out that is always at most twice the stable commutator length of W. Sorry, at least twice the stable commutator length of W. And it also turns out that that is always at least the primitivity rank of W minus 1. And once you look at the picture like this, then you sort of hope to yourself that, and indeed it turns out to be true, that this stable primitivity rank that I've defined fits in down here. It turns out it's always a lower bound, both for twice the stable commutator length and also for the primitivity rank of W minus 1. And another thing, I can tell you some other things. So it turns out that most of these inequalities are sharp in the sense that they're not always equalities. So sometimes these inequalities really are inequalities. This one's sharp, this one's sharp, this one's sharp. I'm not going to give you the examples now, but it's not hard to write. They turned out to be quite easy to write down. Or they're not difficult, at least. So that leads to the natural question, is this one sharp? And that's why the very last thing I'm going to tell you is that actually, although I'd like to think I've got an interesting definition of stable primitivity rank, the truth is that I don't know. And in fact, I'm going to conjecture the opposite. I want to conjecture that actually I haven't given, although I just gave you a very complicated definition, maybe it's a very simple quantity after all, because maybe actually this thing is never sharp. Maybe the primitivity rank of W minus 1 is always equal to the stable primitivity rank. That could be true. And I'd like to think that this conjecture is a win-win. So if it's true, well, then we have this would be a very deep theorem about primitivity rank, and it would tell you that it has this amazing stability property that, it would be a really deep theorem. On the other hand, if it's false, well, then, I'm really happy, because that means that I've given, all of this work I did to give you this definition is worth something, because it's an interesting number. It's going to tell us some new information. Right. So I do have some weak evidence that it might be true. Maybe I'm going to skip over one of those bits of evidence. I'm just going to finish with this one. So there's a related conjecture, which is called Hoya's conjecture. And his conjecture is, if I come back to this this square of inequalities here, Hoya's conjecture is this one here. So Hoya conjectures that inequality. So what is that? That tells us that the conjecture is that twice the stable commutator length of W should be bigger than or equal, should always be bigger than or equal to the primitivity rank of W minus 1. So let me point out to you that if my stability conjecture is true, so the stability conjecture is the statement that this thing is always equality, right? And so in that case, we would get Hoya's conjecture, you see, just by because then we'd have this sort of chain of reasoning, right? We'd have that twice the stable commutator length is bigger than or equal to the primitivity rank of W minus 1. Okay. So the stability conjecture implies Hoya's conjecture. And I'm glad to say that just this year, in 2020, just a few months ago, Cashin and Hoffman checked Hoya's conjecture using a computer on all words in F4 of length at most 16. So that's a pretty huge collection. I think it's millions of words. And they found that Hoya's conjecture was always true. So some evidence that the stability conjecture has a chance of being true too. Okay, that's everything. Thanks for your attention. I'll stop there.
So let's thank the speaker.
Very much.
Now, somebody have some question?
I have sort of question, but it might be sort of more, I don't know, more philosophical than concrete. I wanted to ask, everybody is here maybe?
I can hear you.
Yeah, I want to ask about this actually primitivity rank, because from your definitions, it is only a definition which doesn't involve the fact that element of free group is written as a word. All right, and therefore it one can do it in profinite or pro-p case, whatever you like.
Yeah.
All right. So my question first, whether I'm not sure in the abstract theory this notion, what is it good? So I mean, what goods does it bring for structure of subgroups or whatever? But whether this the results where it is to which this notion is connected can be sort of stated as a conjectures for the profinite to pro-p case. And secondly, I was sort of, when you go on, I was sort of disappointed that stable rank actually does involve it. So my question whether, well, if the conjecture is true, then it wouldn't involve the risk, right? So I would sort of try to hope that the conjecture is true. But if it, my question was whether it can be given actually definition without using the fact that the element should be written as a word.
Oh yeah, no, I think it can. Oh, and when you say I wrote it as a word, what you mean is I wrote it as an element mapping to as a circle mapping to a graph, which is like writing
exactly, and therefore you use that it is bound infinitely many times.
Yeah, you don't really need that. You can. There is a way. Yeah, I think the answer is you can do it without that. So I think you can make the definition in the profinite case. You know, maybe the other thing you want, you know, I don't know, but I don't know if that would have any relationship. I don't think I can prove it's non-trivial in the profinite case. And I don't think I can prove that for primitivity rank either. But what I can tell you is that Puder and Pós-graduação can prove that primitivity rank is, well, actually, yes. So Puder and Pós-graduação have a completely different characterization of primitivity rank, which is all about statistics of word maps. And probably from that point of view, you can give that definition is probably the best definition to use. It's a very complicated definition. It involves analysis, actually. But it makes good sense in the profinite world. And in fact, that definition shows that the primitivity rank is a profinite invariant in the sense that if two words are in the same orbit of the profinite of the profinite completion of the fundamental group, sorry, of the automorphism group of your free group, then they'll actually be, then they have the same primitivity rank. So, did that make sense?
Yeah, it does. Yeah.
But Puder and Pós-graduação's definition is a really, or at least their characterization is a really different and very deep characterization. So that's probably the one to use.
Some other questions?
I have a question. Oh, sorry.
Hello.
Hello, Faz. Just to know, what happens with the stable primitivity rank when you take a primitive element? What happens with those maps?
Yes, so that's going to be infinite. So in that case, that's exactly this case. Yes, thank you for asking that, because I should have said it, but I didn't. In that case, if we go all the way back to this, where is it? If we go all the way back to the definition, there will be no indecomposable immersions in that case, it turns out. And therefore, I will have the infimum of the empty set, and therefore I want to say it's infinite. I mean, you can argue with me about whether infinity is the right number to use there, but you could also call it -1 or something. I don't know what the right number is, but whatever you think the infimum of the empty set should be. But that's what happens there. And sorry, let me also say that's an if and only if. So actually it characterizes primitive elements in that case.
Some other question?
Where does Whitehead sit in this theory? It's a good. So this is about Whitehead's algorithm, I guess. Is that right? So
Well, you mentioned this, yeah.
yeah. So yeah, I don't know. I agree. I was a little. The connection is tenuous. So actually, I sort of said that I'm lied to you a little bit, because I said that primitivity rank was a measure of the complexity of Whitehead's algorithm. And it's not clear that that's really true. But Puder has given a different version has given an alternative to Whitehead's algorithm. And it's not clear if Puder's algorithm is somehow a clever, different way of looking at Whitehead's algorithm, or if it's just a genuinely different algorithm. And it may be that Puder's algorithm is genuinely different. But primitivity rank is a natural measure of the complexity of Puder's algorithm. Okay. So maybe, if I were going to write that in sort of, in characters, what I'd, like a sort of the way, I can write something for you there, which maybe helps to clarify that. So sorry, my tablet is now being very slow. Here we are. So pi of W is in some sense the complexity of Puder's algorithm. And then a sort of question that you might ask is Puder's algorithm equivalent in some way to Whitehead's algorithm? Right. So the honest answer is that I don't know exactly how Whitehead fits into the theory, but this is a different, somehow, this is what it does do is what primitivity rank does do is it measures the complexity of something that seems to play the same role as Whitehead's algorithm, but I don't know if it's the, I don't know if it's, I don't know which one's quicker to run, for example. I don't know, I don't know anything like that.
Okay. Some other question? No? Let me see. Okay. So let's thank again the speaker.